Hi, everybody. Today we are going to continue with our series on resolving cognitive disparity and dispensing with cognitive disparity. So this episode is Ontological Mathematics explains the double-slit experiment. So in the last episode, we solved Einstein's simultaneity paradox, and we examined what he did with introducing cognitive dissonance, cognitive disparity as an institution for how scientists should think about how they do their work. That began with Einstein. So now we are going to resolve that historical mistake. So we did that last time by resolving the simultaneity paradox, and now we're going to do that with the double-slit experiment. Okay, so dispensing with cognitive disparity. Yeah, so just to review, what is cognitive disparity? That is the state of mind where paradoxes have become preferred explanations of phenomena in reality. Of anything, people just prefer paradoxes. And again, this was begun and instituted by Einstein, where he said in his simultaneity paradox that photons can do two different things at the same time. And then, of course, this was continued directly with the Copenhagen quantum mechanics interpretation, where things like cats can be two different things or an infinite number of different things at the same time. So instituted cognitive dissonance has replaced reality with a new hyperreality of cognitive disparity, where differences are no longer different and similarities are no longer similar. Basically, what's happened is that the ability for the mind to discriminate has been removed. And of course, we're always, taught that discrimination is bad. Of course, it's used in the context of racism, but, the general idea is that any sort of discrimination, what's being removed from the human mind is the ability to discriminate at all. Of course, discrimination, just in its definition of being able to tell one thing separately from another, that's the base human mind. I mean, even animals need to do that for food and basic things. I mean, for humans, which are we are absolutely mental creatures, not instinctual hardly at all, just a little bit, but we are absolutely mental creatures. The ability to discriminate, to be able to tell one thing from another thing, to be able to tell what's different, what's the same, that is fundamental to our condition. So if you remove that from the human mind, from human culture, you absolutely destroy humanity and reduce us not even to an animal state. You remove us from existence itself, because even animals perform discrimination. Even bacteria would have to perform discrimination, the ability to tell what is the same and what is different. So we have differences are not different, similarities are not similar. Things can be two different things at once. So Einstein did that, Copenhagen quantum mechanics does that. In climate science, this is a great one. Earth is not flat, but it also can be flat. Photons can be two different things at once. So there's many such examples in the current world. So it's the cessation of thought. It is the total destruction of mind is what is happening. So here's a great quote. This sort of extends from something I was commenting on in my last video. And then this just came up on some feed somewhere, maybe on Facebook or something, and I just thought, well, this really goes to exactly what I was saying in my last episode. So this is really funny. I don't know who this guy is. I suppose this is a book, but this was a really great quote. So he says, "An idiot admires complexity. A genius admires simplicity." This is the only sentence that can be removed from this quote. A physicist tries to make it simple. Well, that's not true, in fact, because, Einstein was the physicist, and he, in fact, made it more complex by making photons being able to do multiple things at the same time. Of course, in quantum mechanics, particles can be, doing multiple things at the same time. So they made it much more complex. So that can be removed, but everything else from this quote we will continue is excellent. Anything that is gaining complexity, the more the idiot will admire it. If you make something more clusterfuck that he can't understand it, he will think you are a god, a genius, because you made it so complicated that nobody can understand it. Well, that is exactly what's happening. That's why I said, if you ever actually tried to publish a simple solution to a problem, the peer review system, the science system, would simply never accept it. The only things which get published are things which are even more strangely complex and make even less sense than the previous existing explanations. That's the only thing that gets accepted nowadays. So that's how they write academic journals, to make others think you're a genius. Yeah, just come up with things that make no sense whatsoever. And that's, like I said, it's terminal. It seems uncorrectable. And so we're just going to have to, at this point, survive on our own, hopefully, if we can. Anyway, yeah, that's a really great Great quote here. He really has insight into what is happening in physics now. Yeah, yeah, it's the physicists that are doing it, though. They're not making it more simple. They're making it more complex. Hockney is, of course, making it more simple. Illuminism, ontological mathematics is making it more simple. So we solved the simultaneity paradox and began reconciling quantum mechanics with relativity in the previous episode. We will continue with the double-slit experiment now. So here's the basic setup for a double-slit experiment. Don't worry about this. You know, this is something that you do in physics. In high school physics is where I first encountered this. Don't worry about it. If you don't know what it all means, you don't have to. It's just, yeah, I can explain. So there's a source coming through here. There's a light source or a water source, and then it goes through. There's two slits right here, which each create a diffraction pattern, and then a diffraction pattern from each of these interferes with each other and creates some other interference pattern, creating all these crazy waves, and then the intensity of the waves on a screen or a recorder device back here just has this sort of intensity distribution. That's all it is. So the light source for light is considered a wavefront. So of course that is true for water, you have a wavefront, but that's not true for photons because photons are actually particles with wave behavior. So here is, you know, the basic idea of a photon. A photon has an electric component and a magnetic component, which are orthogonal to each other and oscillating. And so the photon is a particle, right? The front of the wave is a particle, but the particle has a wave behavior, this oscillation. So basically this particle is the flowing point, and it's basically this flowing point of string theory. It's basically a flowing point which is on the scale of length of the Planck scale. So it's extremely tiny. You could never really do an experiment to see the flowing point because it's just like so ridiculously tiny. But nevertheless, it's a flowing point, which is basically a particle, and it is following this wave trajectory, which is of course, you know, the circling, as we've discussed in previous videos. So it is a point. It's a flowing point, very, very tiny, tiny little string, basically. But so small it's effectively a particle. Anyway, and it follows this wave trajectory, this wave pattern, yeah? So that's individually. An individual photon looks like that, yeah? So the wave interferes with itself. So that's true for water, and it's true for photons when you have a whole bunch of photons going through here, but you still get this interference pattern when one photon goes through at a time. And so that's the big confusion in quantum mechanics for how that can happen. We'll get into that. So they say, is it a probabilistic thing? Is a single photon going through both slits at the same time? You know, probabilistically, and the probability wave is interfering with itself. So we're going to solve that problem. This is important. You get no interference when observed. So if you have an observer at the slits, and this is for electrons because you can't really observe a photon that you're not going through the slits, but you can detect if an electron is going through the slits. So if you observe the electrons going through the slits, the wave interference pattern disappears, and then that's where they get the idea that, oh, observation seems to change the results, and they're so confused by that. Wow, observation seems to get rid of it. It seems to collapse the probability wave, and the probability wave somehow knows that you're observing it, you know? So we're going to solve that problem. Yeah, so they call that probability collapse and other crazy things. But the important point is that the observation is being made at the slits. So we'll get into that. So double slit schematic. So this is for photons. So basically when you have a whole bunch of photons, you have some photons that make it through this tiny little slit and some photons that make it through this tiny slit. And then inside here you get the diffraction plus interference between the diffraction, and it causes this pattern. But the important point to note is that you don't get a wave interference pattern from a single photon getting through. A single photon getting through creates a single detection. Like if this is a photographic plate, or, you know, in modern times a CCD camera or something, you get a single detection, which shows that, you know, the photon really is a particle. It's a tiny particle, and its wavelength is very, very tiny, so it gives you just a single point detection, right? And so what you need to do is build up like tens of thousands or millions even of photons until you get the signal building up. So this is say after, you know, depending on whatever your photon rate was, or the brightness was, say it was really dim, A is 10 seconds, B is, 20, 30, 40, whatever. So after 1,000 seconds, you get, enough signal built up that you can see the interference pattern. But for only a few photons, you can't really tell or see what's going on at all. And so the photons, are single detections at discrete locations in space on the detector. Okay, so when many photons pass through, that's no problem to understand because you just say that they interfere with each other, just like, a water wave does. So even though they're particles, they go through here, and then there's so many of them that they're just interfering with each other, right? So that's no problem to understand. But the problem is when one photon at a time passes through, they still interfere with themselves. How? And so the idea that they came up with is that, and this just follows on from Einstein. Einstein said that a photon can do two different things at the same time at once with his simultaneity paradox. So really, quantum mechanics simply continued with that idea from Einstein and said, well, a photon then goes through both slits at the same time, probabilistically. So, here you have this stream of photons which make it to the upper slit and this stream of photons which make it to the lower slit, and they go through and they interfere with each other on this side. That's fine. But now it's like, well, which photon, I just put it in the middle, but really, it would be the photon up here going by itself, which is supposed to go through this slit, but now it goes through both slits somehow. Or what about the ones in the middle? They're going through both. Like, which photons are the ones that go through both slits now? I mean, so this is cognitive disparity because you're saying that a single photon, which presumably you draw one up here and it was going to go through this slit, but now it goes through both slits in some sort of abstract probability probabilistic fashion. And that is what interferes with itself, is this probability wave. Just because that's how you have to interpret things now, because now you're going with cognitive disparity. So you have to come up with an explanation for that. And so you say, well, there's some sort of on-scene probability wave, and the photon interferes in some sort of abstract way that you can't really explain, but the photon does two different things at once, follows two different patterns. Or you have pilot wave theory. You say, well, there's a pilot wave, a probability distribution, and the photon just sort of like that game Plinko goes through one of these entrances, and then it plays a Plinko game down here, and it interferes with a sort of Plinko game of probability effects down here, and that's what gives you this interference pattern. It's like, okay, but then what is the ontological reality of this probabilistic Plinko game that, yeah, sure, so a photon still goes through either one. It's not that it goes through both. There's an abstract probability field which exists as a result of the presence of both of these slits. And when a photon goes through either this slit or this slit, then it follows that Plinko game of probability, and it's that probability wave Plinko game which causes the interference pattern. But then, like I said, yeah, well, why would that field, how does that field exist separately from the photon itself? So so I'm talking about de Broglie pilot wave, which is actually not accepted really in quantum mechanics. Quantum mechanics really just sticks, modern quantum mechanics really just sticks with the idea that no, the photon travels through both somehow. And well, of course they don't really have it defined very well, what they're talking about at all. We will though. So how is that possible? Probabilistically, well, let's reject cognitive disparity and let's be rational. So photons are real, discrete, and definite things, right? Because a single photon makes a single point detection on your screen. So a photon is a real, discrete, definite thing. We have to reject that objects can be two different things or two different places at the same time, right? So they can only do one thing at a time, and as a result of those two, just statements of reality, you would conclude that probabilism is false. Of course, we won't assume probabilism unless we come back to it, but let's just reject it, right? Let's go with ontological mathematics and rejecting cognitive disparity, and let's say that photons are real, discrete, and definite, and they can only do one thing at a time, because, of course, that's rational. Nothing can actually be in two different places at once, right? So how can they interfere with each other then when they're only one at a time? So let's just state some facts of the matter. So photons, and we covered this in a previous episode, and of course it's all throughout the Hockney God series books. So photons do not experience time or space. spatial distance and time is an illusion for a photon, or spatial distance and time is an illusion actually for us. Photons are the true reality. The mental singularity is the true reality. What we perceive as spatial extension is just sort of a numeric gridding of coordinates, right? We also learned in the last episode that for a photon, their future observer, what to us is a future observer, for them is actually defined as part of their life history. So their observer is defined as part of their life history as soon as they're created. So a photon knows exactly where it's going to go. So yeah, so this is a neat concept. So when you go outside and you look at a star, say a star is 1,000 light years away, right? So when you go outside and you open your eyes and you look at a star at nighttime and you see it, the photons from that star, which left that star 1,000 years ago, from the photon's perspective, those photons, quote unquote, knew that you were going to be their observer. You are the one. Your eyes, your detection apparatus, is what they traveled at the speed of light relative to for 1,000 years. Because for them, that happened instantaneously. When that photon left that star 1,000 years ago, 1,000 light years away, in the reference frame of that photon, there's no space and no time. So it knew, quote unquote, that you were going to be the observer of that photon 1,000 years ago. Now you go out and you open your eyes and you look at it, bang, that life history for that photon is now finished. Because for the photon, that was instantaneous. That all happened instantaneous. There was no time and no space to traverse, right? For us, we perceive what should be a traverse of time and space, but that's actually illusory, right? Because existence is actually a mental singularity. So in the given experimental configuration, you would then have to say that all photons exist timelessly and spacelessly in a lifetime of that configuration. There's no spatial distance and no time for that spatial configuration of the experiment, right? So resolution then, how can we work towards a resolution? So again, a photon does not exist in time. It's timeless. A photon does not exist in space. It's spaceless. And of course, here's the equation which shows that. This is gamma, the Greek letter gamma. It just shows the factor to which time is shrunk and space is shrunk. And so for a photon, which has this speed that we just call c, then its velocity v here becomes c. So you have 1 minus c squared over c squared. So that's 1 minus 1, which is 0. The square root of 0 is 0. So you have 1 over 0, which is infinity. So for a photon's lifetime is infinitely time dilated, which means no time shrinkage, which means that all time for the photon has gone to 0, does not experience any time whatsoever, and space contraction is likewise infinite, and so there is no space for the photon to traverse, either from the photon's perspective, right? So the photon is created, and instantaneously it is in contact with its destination. It knows exactly what its destination is going to be because there's no time and no space for the photon to perceive, because it's infinitely time dilated, infinitely contracted in space. So for a given configuration for which all photons have a defined instantaneous or eventual observer, they interact timelessly and spacelessly with each other in the context of that configuration. So a photon experiences a space-time configuration where all of the other photons exist in that context too. So the space they exist in is structured with all the other photons of the context of that configuration, right? Because for a photon, it's timeless. So that if it's timeless, that means that everything else that ever happened in that configuration is contemporaneous with the existence of any single photon, right? So I'll just repeat that. So in a given spatial configuration, such as this experiment, a photon experiences no time, which means that anything else that ever happened in that configuration is contemporaneous with the photon. So what does that tell you then? Hence, they still interfere with each other because they still see each other, because they see everything else that ever existed in that configuration. So of course, when you have the flood of photons, when there's like billions of photons and they're going through at the same time, well, you just think of it, oh, well, they're interfering with each other because there's enough of them in the present moment to do that. But then you go to the problem of, well, only one is going through at a time. What is it interfering with? And then that's when you come up, well, is it going through both slits at the same time and interfering with itself? Well, only if you believe that things can be two different things at the same time, but that's now cognitive disparity. That's cognitive dissonance. That's not rational. Things can't, nothing can do that. I mean, why would you propose that, right? But if you simply consider what existence is experienced as or like for a photon, there's no time and no space for a photon. So that means that in a given spatial configuration, a photon sees all time in that given spatial configuration, and in all time, there's all of the other photons of that experiment. So the photon still sees all of the other photons. A single photon still sees all of the other ones because they're contemporaneous with it, because there's no time. We think, oh, they're going through one at a time. That's what we think, because that's our experience of reality. But the experience of reality for a photon is that there is no time. So if there's no time, that means that anything else which happened in that configuration is contemporaneous with it. So a photon sees any single photon sees all the other photons which exist in that space for the lifetime of that configuration. And so, of course, they still then must interfere with each other. And boom, you solve the problem. They still interfere with each other. What a simple solution, right? The whole problem here, what's the problem? The problem is trying to figure out how photons can still create this diffraction pattern, or this interference pattern after diffraction, which means that they have to interfere with something. How can you get an interference pattern without them interfering with something? So again, when there's a flood of photons, you just say that they interfere with each other. There's enough going through here at the same time that the top one, and there's a bottom one here, would be say that they just interfere with each other. That's fine, no problem. But one at a time, the problem is, how do you get the interference pattern when they go through one at a time? And so the standard interpretation is, following on from Einstein's introduction of the idea of cognitive disparity, where things can be two different things at once, but then that causes all of this problem that's been unresolved in quantum mechanics. They haven't been able to understand it for, a century now, right? And they're quite proud of that. Even they've simply resolved to being proud. Well, we're proud that we can't understand it, and just shut up and calculate, right? But this is actually now a very simple solution, isn't it? Because we're just acknowledging what a photon's experience of space-time is, which is that it doesn't experience space-time as we do. A photon does not experience that other photons are going through one at a time. It experiences everything all at once that ever could have happened in this experimental configuration while that experiment existed, right? And so that means that the photons, how do you get the interference pattern? That's the big problem. How do you get the interference problem when it seems like there's only one going through at a time? Well, that's not what that's our experience, but that's not the experience for the photons. For the photons, all the other photons are there too. For any single photon of this experiment, all the other photons in the experiment are present as well. So they still just interfere with each other. Boom, solved. You still get the interference pattern. Isn't that nice? Very nice. So electrons too. So electrons also exhibit this behavior. So this seems really troubling, because an electron, is not a photon. But the thing is, an electron is a fundamental particle, and it is known that it has a wavelength. That is a fundamental property of an electron. It's a point particle, a fundamental particle. It's, it's one of the fundamental particles, just like a photon is. So a photon also has a wavelength. They're typically much, much smaller than a photon. They're wavelengths, and so you have to do much more careful experiments to get this interference effect with photons. Really easy to do it with electrons. You have to have really, really careful machining and things like that. But anyway, it's can still be done, and it happens because we can accept that when a lot of electrons are going through, the electrons have a wavelength. But the thing is, it still happens when photons go through, or when electrons go through one at a time. And so, yeah, just finishing this, electrons are fundamental particles, also have a wavelength, and the Pauli exclusion principle suggests that they are aware of all others in the universe, of all other electrons. So that's kind of interesting, right? That's a very quirky, funny property of electrons. Kind of like how for a photon, no space and no time exists, which means that it doesn't it doesn't experience any space or time. For an electron, no electron can share the same energy state as any other electron. But that would imply that that has to be coordinated across the universe instantaneously, right? Well, that's kind of like how a photon behaves, because for a photon, it doesn't experience time or space, which means that everything for a photon is instantaneous. So an electron seems to share in the behavior of a fundamental particle, similar to a photon. and that for this Pauli exclusion principle to apply, it has to apply instantaneously, universally across all space and time. So it implies that any single photon or any single electron is aware of all others in order for that principle to continuously be applying everywhere in space. Therefore, electrons, like photons, must be spaceless and timeless particles too, because after all, they're fundamental particles. Therefore, the same considerations in the results manifest. So everything that I just explained previously about a photon, everything applies just the same to an electron. So it explains a scenario where observations in the present seem to affect what electrons did in the past. You know, observation of photon in the present sort of affects its life history, right? Because as we said, when we were covering the simultaneity paradox, how can a photon know that it's supposed to travel at the speed of light relative to its observer when the observation happens in the future, right? And the solution was that, well, actually, for the photon, the observer is already defined because the photon experiences neither time nor space. So for the photon, its future observer is already defined. That's no problem for the photon. For us, we experience this, time sequence of events, and we're like, how can the photon know to travel at the speed of light relative to the observer, which happens in the future, right? It's almost like the observation in the future of the photon affects the photon's behavior and its speed of light along that path distance in the past, right? But the thing is, for the photon, that was all already defined instantaneously. So the same results then would apply, same considerations would apply to the electron. Right? So that explains. We're explaining and we're solving some of the most profound problems in quantum mechanics right now with ontological mathematical thinking. Yeah? Okay, great. So observed slits. Yeah, so you can, oh yeah, so then they always bring up, well, if you observe the slits, that doesn't happen. But the thing is, you can stand back and observe the slits. I mean, you can do this experiment with photons and you're staring at the slits, right? But you still get the interference pattern, right? So it's not like just staring at the slits. That's not what they mean by observing. You can stare at the slits and you get this interference pattern. So that's not what is meant, right? Observing the slits changes the results. It's a very particular way in which the slits are observed. And so the same reason as simultaneity paradox, because you're not actually observing the photons going through the slits. You're just observing photons which bounce off the experiment, off the plate or whatever this is that come to you. You observe those ones, but the ones that make it through the slits, you're not observing those, right? So if you have an observer detector at the slits, here's the thing. And so this is done with the electron experiments when you're sending electrons through. So we just still have photons, but just think of them as electrons. So the thing about that is that you are changing the space-time configuration of the experiment. You're changing the lifetime of the particles. Why? Because instead of the observation happening at the screen back here, and that is the observation which defines the entire lifetime, and we'll just think about it in photons because it's easier. So this screen back here, the photographic screen, is what determines, as the observer, is what determines the entire lifetime history of the photons, right? But now, how can you detect if an electron is going through the slits? You can only detect if an electron is going through the slits if you have some sort of device that is detecting them. What's a detection? A detection is an observation. So you're completely changing the experiment because now you have an observation happening here, and you have an observation happening here, and then you have a final observation happening here for either of the electrons that come through either that slit or that slit. So now you actually have three observers, one at this slit, one at this slit, and then your final observer on the screen, the camera. And there's 4 lifetimes, right? So you have the lifetime of the electron that is coming from the source and making it to this slit. That's one lifetime. Then you have a lifetime of an electron that's coming from its source and making it to this slit. That's the second lifetime. Then this electron goes from whatever detected it here, a detector. That's an observation. You can't detect something without calling that an observation. So now you have another lifetime from this electron going to this screen and this electron going to this screen. So now you actually have 4 different lifetimes. You have 4 different observations. You've completely changed the space-time setup, the configuration of this experiment. There's way more observations happening, right? So yeah, as I just explained. So this really gets to the point that really in quantum mechanics and in physics, they really have no idea what they mean by the observer, by an observer and the relevance of one. It's not clear to them that making a detection of an electron passing through either one of these slits, that you can only detect something if you observed it. So that means an observer. So you've an observation has happened at the slits instead of only at the screen. So you've completely changed this experiment. It's a completely different experiment, right? So here's a little more close-up view. So this one I pulled from the web. So these are little detectors at either slit. And so like I said, if you have a detector at the slit, a detector at the slit means there's an observation happening at the slit. There's an observation of the electron going through the slit. So having a detector at the slit ruins the diffraction pattern, which would be necessary to get the interference pattern, which would happen in here, because you need the electrons to pass through here, getting to their observer, where this would be the only single observer. So you just get trajectory from source to either slit, then to screen, not diffraction through the slit. So it ruins the, and I just use little scrolls here as detectors. At first I just made this up myself, and then I realized there's probably a better one that I could find online. So what you really need to get that interference pattern is you need diffraction. You need diffraction, and we won't get into why you get diffraction through a slit, but it's related to the wavelength and the wave sort of curving around the edges. I mean, that's some fun physics there, but we'll dispense with that. So you need diffraction. You need a diffraction pattern coming through this slit, and you need a diffraction pattern coming through this slit. And then the diffraction patterns are then what interfere with each other over here and give the diffraction pattern that you record, right? Now, if you have a detector in these slits, that means an observation is happening here. And so you're totally changing the diffraction pattern, because you get the diffraction pattern when these things go through unaffected, when they go through just by themselves and they curve around these slits, curve around the edges, and that creates a diffraction. If you put something here to detect them, well, you're destroying what would be the natural diffraction pattern. You're wrecking it. You're wrecking what should be the diffraction pattern, because you're interacting with the particles here. You're observing them. That means you're interacting with them. That means that the life history of these electrons stops here, not going through here and stops here. The life history only goes up to here and then goes from here to here. And then that you get the traditional classical result, because you've destroyed the diffraction pattern. And so they just continue from their interaction with their observer here, and then they continue on here. And so basically all that is happening is that with a detector here, you're destroying the interference pattern. And by destroying that interference, because you're having an interaction here, an observation, then you get the classical result. So, so yeah, I mean, it's easy to explain. We can explain all this now quite easily. So cognitive accord. So applying ontological mathematical principles results in cognitive accord as opposed to cognitive disparity or cognitive dissonance. So accord, what do we mean by accord? To be in agreement or harmony, to correspond, proper relationship, proportion, harmony, harmonious union of sounds, colors, and especially ideas and thoughts. So it is an expression of the form of the good, obviously. Cognitive accord, what would you call that? Yeah, that is an expression of the form of the good. So let's just switch over to a couple websites here and go through what they say about the double-slit experiments, and we'll see that, oh, now we can easily answer them. So where is that here? So let's start with this one. Hopefully I edit that out, that cough. So one of the most famous experiments in physics is the double-slit experiment. Unparalleled strangeness. Well, yeah, because you interpret things that are impossible, that things can be two different things at the same time. Little particles of matter have something of a wave about them and suggest that the very act of observing a particle has a dramatic effect on its particle. Well, see, this is the thing. They don't even understand what an observation is. They think it's some sort of magical, wonderful thing. Of course, it's going to change. Like an observation, like basically think of baseball, right? I mean, this is important in baseball when you do relay throwing, right? When the outfielder throws to the second baser and then the second baser throws to the home plate, that's faster. I mean, just in that case, right? They do that because it's faster instead of the outfielder throwing all the way to the home base. The point, though, is that they're saying it's so magical that when the outfielder throws to the second base and then the second base throws it to the home plate, oh, that's such a different result, and it's magical, unparalleled strangeness of difference compared to when the outfielder throws it directly to the home base, right? It's like, of course it's different. The second baser intercepted the ball because he had it thrown to him, and then he threw the ball to home base. Of course that's a different result. Of course you get a different behavior. But when it comes to quantum mechanics, they seem to be totally unable to understand what they mean by detections, observations, interactions. Okay, so of course it has an effect on behavior. Of course, observing something, interacting with something, changes its behavior when you're compared to the situation when you're not interacting with it. I mean, that's no different than the outfielder throwing the baseball to home. You get a different behavior in the velocity of that ball, how that ball gets home, if the outfielder throws it straight to the home plate versus if the outfielder throws it to the second baseman, the shortstop, and then to home, right? Of course it's different. Okay, so to start off, imagine a wall with two slits in it, throwing a tennis ball at the wall. Let's just see what's important here. Okay, that's fine. Yeah, so that's the classical result if you have things as big as tennis balls, because something as big as a tennis ball has such a tiny wavelength compared to the size of the tennis ball. Yeah, you can't get tennis balls which interfere with each other. Tennis balls are too big, they can't interfere with each other, so you get the classical result. Now imagine shining light. Yeah, so if you have a wave front like water or, enough photons and you just think of the photons interfering with each other, yeah, they cancel each other out or build up and you get this interference pattern. All right, okay, that's fine. Here's a picture of a real interference pattern. Oh, that's the one that I used. Okay, diffraction pattern. Yeah, okay, yeah. So you need the diffraction pattern first, and then from two diffraction patterns interacting, you get the interference pattern. So now let's go to quantifying electrons. Block one of those slits off for a moment, and they behave classically. Right, okay, fine. Now open the second slit. You'd expect two rectangular strips on the second wall, just like tennis ball. Okay, well the thing is, a tennis ball is huge and has such a tiny wavelength, but an electron is a fundamental particle and has a wavelength that is, on the scale of the size of the electron. Yeah, so you can get an an interference pattern built up from the waves of the electron. That's fine. So yeah, you get that interference pattern. Okay. So saying, how can this be? Wait. As more and more electrons are fired, how can that be? So one possibility, electrons somehow interfere with each other. Yeah, okay, so we understand that because electrons do have a wavelength. That's fine. So here's where they get into the interference pattern remains even if you fire the electrons one by one so that they have no chance of interfering. Okay, well, they have no chance of interfering from our perspective, but from their perspective, they're timeless and spaceless, right? Due to the Pauli exclusion principle, it tells us that that an electron must be a spaceless particle. It is aware of all space at once. So in the experimental configuration, I mean, the same explanation that we went through for photons applies, right? They interfere with the other ones in time. Yeah, each electron still contributes one dot. Yeah, and it builds up over time. That's right. Yeah, because it's still a particle, but it's a particle with a wave behavior. It's the particle that's at the front of the wave, right? That's what it is. The photon particle is the particle, the flowing point that is at the front of the wave. So just as with the electron. The electron is fundamentally a wave phenomenon, but what we interact with is this sort of point particle flowing point that is at the front of the wave. Yeah, so then here, could it be that electrons somehow splits and passes through both at once and interferes with itself, then recombines? Well, that's to meet the screen as a single localized particle. Well, that would be crazy, right? How would it do that? Why would a discrete, especially a fundamental particle, how would a fundamental particle, which is a fundamental unit, indivisible, now magically it splits into two and goes through the screen? Well, we have a much better explanation for that now, don't we? So he says to find out, you might place a detector by the slits. So they have no idea that they're changing the experiment. They have no clue that they're fundamentally changing the entire pattern of the experiment, configuration of the experiment. And they seem to have forgotten that the reason why you're getting interference is because you have two diffraction patterns. So putting an observer at the slit, you're destroying the diffraction through either slit. I mean, what's strange? But it's because they've been infected with this cognitive disparity virus. Given to them by Einstein, so they can never they just can't work it out anymore, Yeah, so somehow the very act of looking makes sure that the electrons travel like well-behaved tennis balls. Well, it's as if they knew that they were being spied on. See, that's the weird. It's as if they knew that they were. What do you mean they knew that they were being spied upon? You had a detector there. You were you're creating an interaction, an observation to occur, which means you're changing the lifetime behavior, the lifetime history of that electron, compared to not observing it. Of course, it's different. It's weird how they're so perplexed by it, right? So it suggests that what we call particles somehow combine characteristics of particles and characteristics of waves. Well, that's not a big deal. We've known that for a long time. But see, they don't seem to know, I guess they don't understand that the particle is the front of the wave. So the particle is following this wave trajectory. Yeah, famous wave-particle duality of quantum mechanics. I don't see why that's so confusing, because, yeah, wasn't it de Broglie that came up with that originally? The de Broglie wavelength, right? Isn't that how we learn it in physics class in high school? The de Broglie wavelength, right? That's him, right? Yeah, showed that all particles have a wavelength. It's not difficult to understand. It's not, you do learn that in high school. But anyway, with ontological mathematics, now we know why a particle follows a wave trajectory, right? Because it's a circling, right? It suggests that the act of observing a quantum system has a profound effect on the system. Well, of course it does. You're observing a fundamental particle, which is the most, a very fine, a very, very, I mean, a tennis ball is, an Avogadro's number of molecules, say, a very, very large number, right? So it's pretty bulky, it's a big thing. A fundamental particle is very, very, very sensitive. Of course, observing, they don't mean observing it from a distance, right? From looking at it back here, with that example with the slits, just staring at the slits from a distance. But see, they've seemed to have confused themselves, and they're thinking that observing it from a distance as the photons go through the slits is what changes it. That's not what changes it. And that's what Einstein introduced too with his homogeneity paradox, that because you can imagine standing back here and drawing the little squiggly lines as photons means that you're observing them and that's what changes them. No, that's not what's happening at all, right? Anyway, so we have, solved that, no problem. I think this one's basically the same thing. Ever hear of the double slit? Two through all waves, whether they're light waves, water waves, okay, good. But light isn't just a wave, it's also a particle called a photon. Well, we've discussed that. It's a particle following, it's the front of the wave, right? What you detect is the wave front as a particle, as a point sort of impulse, right? Turns out even though there's only one photon, it still forms an interference pattern. It's as if the photon travels through both slits simultaneously. No, that's not possible. A discrete real entity cannot be two different places at once, right? So of course here they say just by observing the double slit experiment, the behavior of the photons changes. So they're actually referring to the electron experiment here. And as I said, it's not like you can perform this double slit experiment and you're staring right at the slits and you get the interference pattern. So it's not like observing it from the outside changes it. It's when you have an observer at the slits, which is what changes it, because you're actually interacting there with the fundamental particles. Instead of having those fundamental particles go through and diffract through the slits, now you have an observation happening there, which changes their phase and changes everything, changes their life behavior, and destroys their ability to diffract through the slit. Well, I think this one basically says the exact same things. But anyway, the point is that we can go through sites like this and easily answer all of their confusion now. Okay, and then just one thing here on the wiki page about so the delayed choice thing, that is answered now by the timeless nature, as we discussed earlier. Where is the, path integral formulation. So this is what, who came up with this? It was, Feynman. So Feynman basically did this correct way, but he didn't understand what it meant. And basically what he did was he said, well, let's consider all possible probabilities, all possible paths that the photon can take, and the photon interferes with itself through all those possible paths probabilistically. Well, that math, the approach that you've set up actually still works, but you got to interpret it differently. It's just that all these different paths are now all the actual photons that go through and interfere with each other, but they're not doing it. We think, well, how can that happen when they're going through one at a time? It's like, well, they're not going through one at a time relative to themselves, in their own phase space, in their own experience of existence. there is no time and there is no space. So all of the other photons of the experiment are sitting on top of any other particular photon. And so, yeah, you simply integrate all possible photon paths, and the photons are interfering with each other, right? So that's what's happening. So basically, his formulation would probably be the correct mathematics. You just have to understand that each instance, each possible trajectory is a trajectory that a real photon takes. It's just that it takes it, in the realm of the photon, in the experience of the photon, timelessly and spacelessly. That means that all the other photons of the experiment are there with it. And that's what it interferes with, is with all the other photons of that experiment, because they exist contemporaneously with it, with any given photon, because there's no time or space for any given photons. That means that they're all together, right? Neat, right? So I like that. Okay, I think that was the last bit, and I will just expand myself and say bye to you. Okay, so I think that works. Gosh, I guess I'm going to have to write another book now. Okay, hope you enjoyed that. I'll see you all later. Bye.